This video demonstrates the heat treatment of 3 steel samples, each with different composition. The objective of this task is to investigate how the hardness obtained after quenching is influenced by the steel's carbon content as well as other alloying elements. Additionally, as part of your investigation, you will examine the correlation between hardness and tensile strength using an appropriate standard. Steels are quenched and hardened to improve their mechanical performance. Quenching increases the hardness and strength by transforming the microstructure to martensite, which is very strong but also brittle. This property is essential in tools and components where the wear resistance and load-bearing capacity are critical. The 3 steels used are TOH, a tool steel that is oil hardenable, 4140, a chromium-molybdenum alloy steel, and 4023, a low carbon mild steel. The TOH sample also has a hacksaw cut on its side to act as a deliberate stress concentrator. This makes it easier to observe a brittle fracture behavior during testing. Each of the samples was supplied with a mill test report. An MTR is critical in engineering practice. It certifies the material's composition, its mechanical properties, and ensures full traceability. For assessment purposes, this gives confidence that the steels are of the correct grade, allows for verification of chemistry, example the carbon content, and ensures that the testing data can be related back to the supplied batch. When working with a kiln, safety is the top priority. Correct personal protective equipment must be worn at all times. This includes a leather apron to protect against sparks and hot scale, heat-resistant gloves, a face shield to protect from radiant heat and splashes, steel cap boots for foot protection. Metal tongs are also essential for the safe transfer of the red-hot samples from the kiln into the quenching media. The first step is placing the samples into the kiln. The door is then closed and the heat treatment program is started. The kiln is programmed to gradually heat the samples to 800 degrees Celsius over approximately 1.5 hours. Once at temperature, the samples are held or soaked for 20 minutes. Gradual heating reduces thermal stresses, which can otherwise cause cracking or warping. The soak time ensures that the entire cross-section of the sample is uniform at the target temperature, making the subsequent quench consistent and reliable. The samples are removed one by one from the kiln and quenched in water within 10 seconds. They are gently swirled in the quench bath to reduce vapor formation on the surface. When hot steel samples first enter the water, a vapor blanket forms around it. This vapor layer reduces heat transfer and can result in uneven cooling, leading to soft spots or distortion in the sample. Swirling the sample breaks up the vapor layer, ensuring rapid and uniform cooling. At 800 degrees Celsius, the samples were quenched within 10 seconds. The continuous cooling transformation diagram, or CCT for short, shows this rapid cooling curve in red. By comparing this curve against the transformation lines, we can predict the microstructure that forms. For the TOH steel, the diagram shows martensite is expected. A CCT diagram is a graphical representation of how microstructures form under different cooling rates. As part of this task, you must plot the cooling curves for each sample and predict the likely microstructure that develops, for example, martensite, bainite, or pearlite. The TOH sample is placed in a vise and struck with a hammer. The sample fractures in a brittle manner due to its martensitic structure and the stress concentrator notch that was cut into the sample previously. The fracture surface is inspected. It shows a granular, crystalline appearance typical of a brittle fracture, with no evidence of plastic deformation. The grain structure can also be observed. All three samples are checked with a file. The TOH in 4140 resists filing, an indication of martensite and high hardness. The 4023 allows the file to cut easily, showing it has remained relatively soft. The next step is to verify the hardness using a Rockwell hardness tester. This machine measures the resistance of the material to indentation under a specific load. The machine has been calibrated by a NADA accredited organisation, ensuring measurement traceability and confidence in the result. The machine is set to Rockwell C scale. This involves applying a 150 kilogram load with a diamond cone indenter. The TOH sample is prepared and the hardness test is carried out. Any surface scale is removed using the file. The TOH registers a hardness of 59.1 on the Rockwell C scale. This high hardness value confirms martensitic transformation and suitability for tool applications requiring wear resistance. The 4140 sample is tested in the same manner. The 4140 sample recorded a 54.6 on the Rockwell C scale. This is slightly lower than the TOH, reflecting its alloy and carbon content. The result still indicates a high hardness suitable for structural and mechanical components. Since the 4023 is much softer, the machine is switched to the Rockwell B scale. This uses a reduced major load of 100 kilograms of force with a 1/16 of an inch steel ball indenter, appropriate for softer materials. The 4023 sample is tested under the Rockwell B scale. The result is 63.9 on the Rockwell B scale, confirming that the 4023 is significantly softer than the TOH and the 4140. This correlates with its lower carbon content and its inability to form martensite under the same quenching conditions. As part of this assessment, you are required to convert the Rockwell hardness value into an approximate tensile strength value using the standard reference tables. You must also discuss the relationship between carbon content, hardness, and tensile strength. This concludes the heat treatment practical. If you have any questions, please reach out to your assessor. We're here to help.